Hello and welcome. Today we are going to do math. We are going to look at what an infinite series is. This content can be found in section 9.2. And in this video, we are going to define what an infinite series is. And I'm going to stop saying that word infinite as we proceed. I'm just going to be referring to infinite series as a series from here on out. In talking about what an infinite series is, we're also going to define what a sequence of partial sums is. And then we're going to talk about whether a series converges or diverges. And to test whether a series converges or diverges, we're going to use today one of three tests. We're going to learn about the geometric series test, the telescoping series test, and the Nth Term Test. And we get a little bonus one there. The Nth Term Test Contrapositive is you'll learn to be quite powerful. A contrapositive, once again, is if the statement P implies Q is true, then the statement not Q implies not P is true. All right, and of course, as always, as we proceed through these tests and as we proceed through these definitions, we'll do some examples along the way. All right, but without further ado, let's do some math. All right, so what the heck is an infinite series? All right, and what we're going to use is just the term series. Definition. An infinite series is the sum of an infinite sequence. All right, this is important. An infinite series is the sum of an infinite sequence. When I say, hey, what is this series? I'm asking for a number. An infinite series is a number, right? Unless, of course, it diverges and then it's infinity, not a number. But an infinite series, I'm going to put in a box, an infinite series, a series, is a number or divergent. Right? It converges to a number, and we say the series is a number, or it is divergent. Box. Very bad box. Example. Right, take the sequence a sub n equal to 1 over n squared. This is not a series. It is a sequence. All right, this series, I'm going to write it in the following way. A little curly bracket. The first term of the sequence, plug in 1, you get 1 over 1 squared, which is 1. If you plug in 2, you're going to get 1 over 2 squared, which is 1/4. If you plug in 3, you're going to get 1/9. Then you're going to get 1/16, dot, 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 1 over n squared, dot, dot, dot. This notation is what Mr. Schwartz used in his previous video. This is a sequence, not a series. Yes, a series. The following is what I mean when I say what is the series 1 over n squared. Sigma notation. N is equal to 1 to infinity of n squared. This is adding up to something, or it's divergent. This thing here at the bottom is a series. Right? We don't know what this number is. I mean, we can potentially figure it out, right? But this is a number. This is a series. This over here is a sequence. We're slowly looking at the differences between what we mean by a sequence and what we mean by a series. Let's inspect this further. I'm going to go ahead and take what we got here to the next page. Boom, boom, boom. I'm going to go ahead and erase my yes, a series just so I'm a little bit more clear. The top thing, once again, is a sequence. This bottom thing is our series. All right, so how do I figure out what this number is, or how do I figure out whether or not this thing diverges or converges? Enter a new term. A sequence of partial sums. Written capital S, sub n. Now, of course, we could change our notation to be whatever we want, but this is common notation. Capital S sub n. A sequence of partial sums is the following list. S sub n is equal to the sum of n equals 1 to 1 of your sequence, comma, n equals 1 to 2 of your sequence. All right, so you are summing up to 1. The next term, you're summing up to the second term. The next term, n equals 1 to 3, all the way up to infinity. What does this look like for our example? It's a terrible arrow. Let me try that again. That's a little bit better. What does this look like for our example? Well, the first term in our sequence is 1. The second term in our sequence is 1/4. So the second term in our sequence of partial sums is going to be the sum of the first two terms. 1 plus 1/4. That's going to be 5/4. Right? The third term is going to be 1 plus 1/4 plus 1/9. I have done this already. I have 49 over 36. All right, I totally wrote that weirdly. The fourth term is a question I'm about to ask in the quiz of this video. Right, but then so on and so forth. Right, that next term ended up being, for those who want their answer, 205 over 144. That's just 1 plus 1/4 plus 1/9 plus 1/16. So we're building a sequence of partial sums. Right? This is the sum of what I've written right here, but just up to 1. The second term is if I had summed the first two. First 3, first 4, first 5, first n, first, and we keep going. This is an infinite sequence. This is why we reviewed sequences in the previous video, because we're going to be looking at things called series. We're going to be trying to figure out whether series converge or diverge, and we need to understand sequences to be able to do this. Right? We're defining a series based on a sequence of partial sums. So what do I mean by that? What the heck is the relationship between the series, the thing I started with, and this new definition, a sequence of partial sums? Well, given the infinite series forgive me how I write all my symbols, the infinite series n to infinity of a sub n, and its sequence of partial sums, S sub n, if the limit as n goes to infinity of this sequence is a number, then the series a sub n to infinity, n equals 1 to infinity, converges. And converges to L specifically. Woo! What we are embarking on, the journey that we are heading towards with many different series tests, 3 of which we're doing today, is going to be looked at through the lens of the sequence of partial sums. If we can take a series, and then look at its sequence of partial sum rule, we might be able to take the limit of that. Or we might need to do specific things like Mr. Schwartz talked about, like finding a function that models the sequence, since we can't do calculus on discrete things. But we're going to be looking at sequences to understand these new numbers, these series. We can't always find a rule for the sequence of partial sums, but sometimes we can, and that is where our first test comes in. The geometric series test. We're going to be looking at a geometric series. This is a little bit of a review. but we have a rule for geometric series, for the nth term of a geometric series, which is great because then we can look at the sequence of partial sum. We can find out if it converges, what it converges to, and we are in business. We can very intensely, I guess, look at the geometric series. The geometric series is nice in that it is pretty easy to understand. This will not be the case for things that do not behave geometrically. But let's go ahead and look at this first test, test number 1. Here is what a geometric series is. Sum n equals 1 to infinity. You'll often see that these are just not written, and the context will imply where you start and where you end. So the context here, I'm going to start at 1. But a geometric series, we have a sub 1 times some ratio between terms raised to the n minus 1. Right, so this is our first term, and then when we plug in 1, 1 minus 1 is going to be 0, and then r to the 0 is 1, so our first term is a1, all right, of the sequence of partial sums. Right, if we look at the sequence of partial sums, our first term is a1. And then our second term, we're going to plug in a 2. We're going to get r to the 2 minus 1. That's going to be 1. And so our second term is going to be a sub 1 times that ratio. Our third term is going to be times that ratio twice, etc. Oh my gosh, I made a classic blunder, and this is actually a great learning experience. I have not written the sequence of partial sums. I have written the sequence, right? The sequence of partial sums. Let's go ahead and write that. That's going to be a sub 1, comma, a sub 1 plus a sub 1 r. The third term will be a sub 1 plus a sub 1 r plus a sub 1 r squared, comma, dot, dot, dot. So I'm actually kind of glad I made that mistake. Mistake was made. Right, so that I'm showcasing the difference between what a sequence and a sequence of partial sums is. All right, we have ourselves a series. Right? Maybe this converges, maybe it diverges. That is kind of the question that we're answering today. We have a sequence. Right? That is just the sequence. We have the sequence of partial sums. And what we want to figure out, converges versus diverges, is based on this sequence. What is the limit as n goes to infinity of the sequence of partial sums? Is it a number? Does it diverge? That is what we are trying to figure out. Right? Before we figure out how it diverges or converges, let's look at a real example with numbers. N equals 1 to infinity. Optional to write those two things. It's insinuated 1 to infinity unless otherwise written that way. We'll have our first term to be 2, and then we'll have our ratio to be 1/3. And let's see what this thing looks like. So our sequence, let's look at all the different things, the ways we can look at this. So our sequence is 2, and then it's going to be 2 times 1/3, which is 2/3. Then it's going to be 2/9, and then 2/27, dot, dot, dot. Right, that is our sequence. Our sequence of partial sums is going to be 2, comma, 2 plus 2/3. Sorry about that, 8/3. And then our third term is going to be 2 plus 2/3 plus 2/9. I've done this in advance. We have 26/9. Right. Then the fourth term will be these 4 things added up: 2 plus 2/3 plus 2/9 plus 2/27. I've done this in advance. It is 80/27. And that is our sequence of partial sums. So what is this thing? What as n goes to infinity, what is this sequence approaching? Is it increasing without bound, or is it going towards a number? Well, if you look at the decimal approximations of these 4 numbers, you can kind of make an educated guess. All right, let me write this again. All right, 2. 8/3. That's like just less than 9/3, which would be 3. So this is like, well, it is 2.6 repeating. But it looks like we're getting closer to 3. This is just less than 3. Sorry for my lazy notation. This one, 81 over 27 would be 3. This is just less than 3, but bigger than the previous term. Once again, sorry for my my poor notation. But the next term is going to be just less than 3. It's going to be one denominator unit away from being 3. So it looks like the limit of the sequence of partial sums as n goes to infinity is 3. We haven't proven this rigorously, but it certainly looks like this thing is approaching the number 3, which would then mean that this series is equivalent to the number 3. There has to be a better way to do this problem than by just inspection. And enter the geometric series test and its proof and its value. We want to prove when this series converges, when the limit of the sequence of partial sums is a real number and not a divergent sequence. That is what we want to prove. Prove when a geometric series converges. Before we do this problem, I do want to say that this value r is kind of the important number. What is r and what is its relationship, r's relationship to 1? Right? If r is less than 1, then my terms are going to be decreasing. If r is greater than 1, my terms are going to be increasing. So I think we can safely say that if r is larger than 1, this thing is going to explode. And if r is less than 1, then things are kind of confusing. If r is 1, then the sequence is going to be a1, comma, a1 plus a1, comma, a1 plus a1 plus a1. That thing is going to diverge without bound. So I think that the relationship to 1, the ratio's relationship to 1 is the key here. And it feels like if r is less than 1, this thing is going to converge. And if r is 1 or if r is greater than 1, then this thing is going to diverge. All right, but let's use a very clever proof of what I've been saying and when a geometric series converges. So we care about the sequence of partial sums. So S sub n, the nth term in the sequence of partial sums, that's going to be the first term plus the second term plus the third term plus the nth term, all the way up to the nth term. We have the first term, second term, third term, and the nth term has a power of n minus 1. All right, here's where the cleverness comes in. I'm going to take this number and I'm going to multiply both sides of this equation by r. I'm going to get r times the nth term in the sequence of partial sums. And then a1 is going to now have an r. a2, and you know what, I'm actually going to write this in a little bit in a more parallel way. The first term is going to have an r. The second term is now going to have r squared. The third term is going to have an r cubed. The last term is going to have an r to the n. Here's where the cleverness plays a role. I'm going to subtract these two equations. Right? My left-hand side is going to be the sequence of partial sums minus r times the nth term in the sequence of partial sums. The nth term in the sequence of partial sums minus r times the nth term. And then I'm subtracting these, so those are going to go away, those are going to go away, those are going to go away, and those are going to go away. I'm going to be left with the first term minus a sub 1 times r to the n. I can solve this equation regardless of how many terms I have in my sequence of partial sums. I have now eliminated all but 2 And I can solve this equation for S sub n. I'm going to factor out an S sub n, 1 minus r, factor out an a sub 1. I'm going to get a 1 minus r to the n. And then doing a little bit, here's an imply symbol. Doing a little bit more algebra, I'm going to get S sub n is equal to the first term times 1 minus r to the n over 1 minus r. I now have an explicit rule for the sequence of partial sums. I can take a limit. I can find out when this thing converges and when this thing diverges. And not only that, I can find out what it actually converges to. And let's look at that. The limit, not lin, of the sequence of partial sums as n goes to infinity, that's going to be the limit as n goes to infinity of a sub 1 times 1 minus r to the n over 1 minus r. All right, using limit rules, anything that doesn't have an n in it and it's and we're dealing with a product, I can pull it out. The a sub 1 can come out, the 1 minus r can come out, and then I had the limit as n approaches infinity. Sorry, the sensitivity on my drawing pad messes up in this region of the page, so that's why I'm always messing up there. The limit of 1 minus r to the n. Right? This thing is kind of easy to look at. And it takes us back to what I said. It's all about r. And let me write this over here. When r is greater than 1, the limit as n approaches infinity of 1 minus r to the n, if r is greater than 1, this term is exploding. This limit here is going to diverge. Well, let me say this. The limit here is infinity, and this limit is infinity, so the series diverges. Right? When r is equal to 1, this limit is going to 0, but we can also remind ourselves why we're doing this. We care about the series. The series will diverge. Right? A constant sequence, if you sum up those terms, it increases without bounds. So the series diverges if r is equal to 1, even though this limit is going to be equal to 0. Right? If r is less than 1, this limit goes to 1, and so the series is going to be equal to 1 minus 0, that's 1. For r less than 1, this is going to be 1. 1 times a sub 1 over 1 minus r is that. All right, so when r is larger than 1, the limit goes to infinity. The series diverges. It is not a number. If r is equal to 1, the series diverges not based on this limit, but based on just adding up a constant term over and over and over again. And then if r is greater than 1, oh, and I should add something, but I'll add it in just a second. If r is greater than 1, if r is less than 1, this is going to be your limit. This is what your series is going to converge to. What I should add is absolute values here. Right? Because if things are negative, if r is less than 1, but also less than -1, then you're going to diverge. So I need these absolute value signs. If I jump back to the problem we were doing earlier, boom, boom. Does this in fact equal 3? Well, what's the first term? 2. What is the ratio? 1 over 3. 2 over 1 minus 1/3, that's 2/3. The 2's are going to cancel. The 1's going to pop up. We get 3. So this does in fact converge to 3. This series is equal to the number 3. All right. With that said, let's proceed. We now have our first of what you will learn to be many tests, the geometric series test. If it's a geometric series, not only can we find that it converges, but we can also discover what it converges to using this formula down here. All right. If that ratio is larger than 1, if the magnitude of your ratio is larger than 1, then it's going to diverge. If it is 1, it diverges. If it's less than 1, we are in business. Let's keep going. So Our second test, test number 2, is the telescoping series test. It's not referred to as a test in the book, but I'm just going to call it the telescoping series test. But we're going to be looking at series that telescope. Now, if you think way back to when people actually used, I guess, telescopes the way, no, we use them a little bit different now, but a telescope kind of looked like this. There's a lens at the top. Okay? But the reason why we call the following series a telescoping series is because these things used to collapse on themselves. This would end up looking like this. And the whole, all the layers are inside of itself. This is the basis of what a telescoping series is. Here's an example of a telescoping series. Look at that, I'm starting at a different number this time, but that's not that big of a deal. N squared minus n. All right, let's inspect this further. I actually encourage you to do this every single time. Let's write out the sequence, 1 over n squared minus n. Let's write out the sequence of partial sums, and then let's start to try to figure out what this thing is converging to or if it's diverging. All right, so the sequence, if I plug in 2, my first term is going to be 1 divided by 4 minus 2, that's 1/2. My second term is going to be 1 over 9 minus 3, that's 1/6. My next term is going to be 1/12, and then that's all I'm giving you. The sequence of partial sums, I'm going to be adding these things up, so 1/2 is the first term. The second term is 1/2 plus 1/6, which ends up being 2/3. The third term ends up being 1/2 plus 1/6 plus 1/12, which ends up being 3/4. 1, 2, 3, 2, 3, 4. Interesting. The next term, I'm just going to go ahead and write it even though I didn't give you the sequence. The next one is 1/2, 2/3, 3/4. The next one's going to be 4/5. Interesting. There's a pattern appearing. Right. Writing out the sequence of partial sums is clever, I think, because noticing a pattern is a strategy that is often used. Right. Now that I have the sequence of partial sums, I can kind of make a conjecture. I think this thing is going to be equal to 1. I think this is going to be equal to 1 just based on looking at my sequence of partial sums. But I want to figure out what this is analytically. I don't want to just think the answer is 1. So what can I do with this? How can I find a rule for this? Like it looks like it's going to be, I don't know, n minus 1 over n. That's like, these two things are a little bit different. This is the sequence of partial sums. This is the nth term. I probably should have a little bit of a different notation, but hopefully this makes sense. The nth term, it looks like it's going to be n minus 1 over n, right? Because when I plug in 2, I get 2 minus 1, 1 over 2. Cool. When I plug in 3, I get 2 over 3. Cool. When I plug in 4, I get 3 over 4. This looks like the rule. Right? And if I simplify this a little bit, I'm going to get 1 minus 1 over n. Okay, and I can take the limit of this. I'm going to get 1. How can I show that this is actually the rule? Right? This is a conjecture. Well, here's where my intuition goes. I have 2 fractions here. I have 1 fraction up here. Maybe I can break this thing up into 2 fractions somehow. Let's use partial fraction decomposition. So let's see, 1 over n squared minus n. That's equal to 1 over n times n minus 1. All right, which is going to be equal to something over n plus something over n minus 1. Multiplying both sides of this equation right here by n times n minus 1 is going to give me 1 is equal to a times n minus 1 plus b times n. And setting my a, let me actually write this whole thing out. That's how I like to do it. Minus a plus b sub n. A plus b is going to be 0. And a negative a is going to be, 1. All right, so negative a is going to be 1. So a is equal to negative 1. Knowing this, back substitution, b is going to be 1. And then applying those things up here, I am going to get that 1 divided by n squared minus n is equal to negative 1 over n plus 1 over n minus 1. Interesting. Okay. All right, so based on this, we have that the series of n equals 2 to infinity of 1 over n squared minus n is going to be equal to the series n equals 2 of 1 over n minus 1 minus 1 over n. Let's use this to write out the nth term of the sequence of partial sums in a different way. So we have, plug in 2, we get 1 over 2 minus 2, 1 over 2 minus 1, which is 1 over 1, minus 1 over 2. That's the first term. Plus the next term, let's plug in 3, 1 over 3 minus 1, that's 1/2, plus, minus. Keep doing that. 1 over 3. The next term is going to be 1 over 3 plus, did it one more time. 1 over 4. All right, that's going to keep doing this like 1, 2, 2, 3, 3, 4 thing all the way up until our last term, which is, well, this is the nth term. The nth term, so when I plug in n, I get 1 over n minus 1 minus 1 over n. This is a telescoping series. Look what happens here. The negative 1/2 and the 1/2 cancel. The negative 1/3 and the 1/3 cancel. The negative 1/4 and then there's going to be a 1/4 in the next term cancel. Right? In the previous term to the last one, the 1 over n minus 1 and the 1 over n minus 1 are going to cancel. And I'm left with 1 minus 1 over n. I'm left with 1 minus 1 over n. That's what I had on the previous page. Well, not the previous page, several pages ago. 1 minus 1 over n. That was my intuitive nth term. Here I'm using the fact that this sequence is, this series is telescoping to derive this formula. All of these terms collapse in on themselves like a telescope. All of these terms collapse in on themselves like a telescope. We have a telescoping series. And then I can take the limit of this thing, boom, the limit of s sub n as n goes to infinity. That's just the limit as n goes to infinity of 1 minus 1 over n. That thing goes to 0. This thing is equal to 1. Therefore, this is equal to 1. We converge to 1. Wonderful. Always be on the lookout to see if your series is telescoping. When is it telescoping? Usually when you have some sort of partial fraction looking thing. Can you use partial fraction decomp? It might be a telescoping series. All right, let me reiterate. Our job today is to figure out whether these series converge to a number or if they diverge. And we can use, so far, the geometric series test if our series is geometric. Or if we have some fraction stuff going on, there's a potential for using partial fraction decomposition and then identifying the series as telescoping and using that to our advantage. We are figuring out if a series converges or not. All right, so we have one last test for you. The nth term test. All right, and we've been talking about convergence for the most part of this video. The nth term test, that's going to be our friend if we want to just figure out if something diverges. And the reason for that will be clear in a moment. But before we do that, I have a theorem for you. Now, we've talked about how if I'm adding up the same thing over and over and over again, that series will converge. If I have the series of like 1, 1 plus 1 plus 1 plus ... forever, that is clearly going to diverge. So, theorem. If you have a series and you know that it converges, if this series converges, if this series converges, then the limit as n goes to infinity of the sequence, not the sequence of partial sums, not the series, the sequence itself, better go to 0. Right? If this thing is going to converge, then the sequence that is embedded within this series better be going towards 0. If it's going towards anything else, if it's going towards 0.1, if it's going towards 10, if it's going towards a number, then ultimately I'll be adding that number up, or numbers close to it, up forever. And I will be able to surpass any number you choose eventually. Right? So in order for something to converge, the sequence better be getting closer and closer to 0. The things that I'm adding up better be getting infinitesimally small eventually. If the series converges, then the limit of the sequence embedded within the series better be going to 0. All right, I want to prove this thing. I don't want to just talk it out. But in order to prove this thing, I'm going to introduce a quick little theorem. Right, I call it the Conga line theorem. All right, and it states the following equality. All right, this equality is true, and the idea of the Conga line theorem is that wherever this sequence of partial sums goes, the terms right behind it are going to the same place. So if this limit is equal to L, then this limit is also going to be equal to L because we can go infinitely far out. Right? If I want to get arbitrarily close to a specific number, if I claim that this gets arbitrarily close to a specific number, if I go one more term out, this will be just as close as I previously wanted. So this equality holds, the Conga line theorem. The reason why it's called the Conga line theorem is because if you imagine the Conga line dance. Let me try to draw better stick figures here. Wherever the first person goes, the others will follow. Right? That's the idea behind this. So we're going to use this fact to prove if a series converges, then the sequence that series is constructed by must be going towards 0. All right, if the series converges, then the limit as n goes to infinity of a sub n is equal to 0. Proof. All right, I've just been told that the series converges. So proof, the series converges. What do we know since the series converges? Well, how do we define a convergent series? The sequence of partial sums. Actually, let me go back a little bit. The limit as n approaches infinity of the sequence of partial sums is equal to some number. Let's call it L. But we also know that the nth term in the sequence of partial sums is equal to, let's get that Conga line theorem in here, the previous sequence of partial sums, the previous term in the sequence of partial sums, plus the nth term. Take a second to understand this equation. All right, so let me go ahead. And take the limit of both sides. The limit of this as n goes to infinity is equal to the limit of this. minus 1 plus a sub n. All right, okay. We have just established that the left-hand side limit is equal to L. So let me go over here. We have L is equal to the limit as n goes to infinity of s sub n minus 1 plus a sub n. But apply the Conga line theorem. Right? This thing also goes to L. L is equal to L plus the limit as n goes to infinity of a sub n. Right, I'm breaking up this limit, but that's valid. That's a limit, a law that is applicable. Right, so doing a little bit of algebra here to subtract L on both sides, and we are in business. 0 is equal to the limit as n goes to infinity of a sub n. Given that a series converges, the limit of the sequence that constructs that series must be going to 0 as n goes out to infinity. Why do I care about this theorem? Right, it's not telling me about convergence. I am given convergence. Right, I want to be able to figure out convergence. Well, the contrapositive. Right, if P then Q. Right, if that is our theorem, then if not Q, then not P is valid. What is that for us? Well, if our theorem is if the series converges, then the limit as n goes to infinity of a sub n is equal to 0. That's theorem 1. Theorem 2, the one that we actually care about. If the limit as n goes to infinity of a sub n is not 0, then a sub n does not converge. I said a sub n, the series does not converge. And in other words, I'm going to go ahead and cross that off and just say the series diverges. Right? The nth term test is a test for divergence, which is awesome because if I say, hey, does this converge or diverge? If you can just look at the sequence real quick and determine that its limit is not 0, you're done. It diverges. That series is garbage. Throw it out. So this is a very powerful test right here, the nth term test, for determining not convergence, but divergence. It's a test for should we waste our time on this series or not. But this is a really important moment for me to say that there's a red flag that needs to be waved. Red flag. Red flag. And that is the contrapositive is true. The converse is not necessarily true. True. If the limit as n goes to infinity of a sub n is equal to 0, this does not imply that the series converges. Does not imply. A quick example is one that you've seen before. 1 over n. N equals 1 to infinity. 1 over 1 plus 1 over 2 plus 1 over 3 plus ... This increases without bound. This diverges. But quickly look at the sequence. 1 over n. As 1 over n goes to infinity, this goes to 0. Right? But the series diverges. Right? If the limit of the sequence is 0, it does not imply that the series converges. We are using the contrapositive. If the limit is not 0, then the series does not converge. Number 57 is a great example of this using the nth term test. So we have the series of n plus 10 over 10n plus 1 using the nth term test. The limit as n goes to infinity of the sequence. The limit as n goes to infinity of the sequence. Right, this is going to be, just doing some limit tricks, we're going to get 1 plus 10 over n divided by 10 plus 1 over n. I'm dividing each term by n. That's going to go to 0. That's going to go to 0. We get 1 over 10. 1 over 10 does not equal 0. So, by the nth term test, the series diverges. And we're done. We are testing for convergence and divergence, and we now have 3 tools to do this. Let me fly back to the first page and do some 6, 5, 4, 3, 2, 1, and then do some overview, just so that we can kind of put this all into context and talk about what's to come. This is section 9.2. Right, we talked about what a series is. It is a number. If the sequence of partial sums converges to a number, then the series converges to that number, right? So the series is a number. We're using the sequence of partial sums. To find out if a series converges, today we use the geometric series test and the telescoping series test. The geometric series test says that a geometric series converges to the first term divided by 1 minus the ratio. The telescoping series says that if we can determine that the series telescopes, then we're going to lose a lot of terms. We're going to have a 1 term minus the last term, and then that is potentially going to converge to something. And then we talked about the nth term test, which isn't exactly a convergence test. It's a divergence test, but it's nice because we are going to learn that checking for convergence and divergence in certain series can be very difficult. But if we can quickly say that something diverges, we can move past the problem and get on with our lives. So knowing when something diverges is just as nice as when knowing something converges, because we'll know that it's useless to us. I hope that the examples in this video were helpful in understanding these 3 tests, and there are many more tests to come. I believe we're going to get roughly 10 tests, and they will get more difficult as we move forward, but these 3 will pop up here and there throughout the coming weeks. So hopefully all of this made sense. If you have any questions, bring them to class. Mr. Schwartz and I will help, and I hope you enjoyed some calculus today. See ya.